And then let's look at a particular choice. Let me choose that all the alphas are 0 except for alpha 2. So alpha 2 is non-zero and the rest are 0. Then we have the characteristic polynomial S2 is the mass term. And if you remember what that is, that was precisely k mu nu squared minus k mu nu k mu nu. And then you put this in, you get minus 1/8 h mu nu squared minus h mu nu h mu nu. And that's precisely the Fields-Pauli mass term. And so we see that these functions, these symmetric polynomials, this function of k, are precisely the unique nonlinear completion of the Fields-Pauli mass terms that you can have. There's nothing else you can write down as long as you're considering actions of this form. Then you can play the game of thinking about whether the kinetic term could be different, and so on and so on. But I think Rachel might mention that later, but it turns out that there are problems against that. Okay, so I almost finished. We just go for 1 minute more. So that's fixed the theory now. The theory is uniquely specified. In the Stukovec form, it's a fully covariant theory, and we know that it corresponds, when you flip the turbo around Minkowski space, you get consistently a massive gravity theory. And I think Rachel will talk more later about the proof that this is fully ghost-free. But let me just tell you now what the decoupling limit of this theory looks like, and you'll see that indeed it is a Galilean. And so what we looked at already is the leading order of the decoupling limit, where we take g to be eta, and f is this combination in terms of capital pi. And then in that case, this is a total derivative, so that gives you 0. So to get the first non-zero term, you have to go to subleading order, where you expand g to first order in h mu nu, and then include that contribution. And the subleading order term is finite, and as promised, the decoupling limit of that theory is precisely a Galilean specific form in which the entire kinetic term only arises from this thing expanded to linear order in h, and then you get a superposition of coefficients. These xn's that I talked about before, built out of the capital pi's, minimally coupled to matter. So these xn's are exactly the same things before, and the cn's there are just linear combinations of the alpha n's up here. It's not very interesting what combinations there are. There's linear combinations. And so that's the decoupling limit theory with this helicity 2 and the helicity 0. You can also derive the contribution from helicity 1, which is slightly messy, but I'll ignore that. You see, as expected, it gives you Galilean theory. And this theory is ghost-free in the decoupling limit in the sense, ghost-free in the Gretzky sense that the equations of motion are second order. And what that really means is that this truly propagates no more than 5 degrees of freedom, at least in the decoupling limit. And I think Rachel will explain later how that's true in the full nonlinear theory. So I better end there.
Other questions?
So we have the latest theory for photon, massive photon, or
Right.
other higher speed. So the general moral is that if you want to measure the mass of a particle, actually you can never experimentally make sure that it's the mass is scale.
Right. That's right.
So there's always a way to.
That's right. We don't know. That's right. We don't know the photon is massive. Is massless. But the difference is what we don't know how to do. In the case of gauge theories, we know how to Higgs them. So we know how to write down theories in which the mass acquires naturally. What we don't know here, what I'm doing is writing down the theory in the Stuckelberg form. Now, and in the case of the gauge theory, the Stuckelberg field is essentially the phase of the Higgs field, because that's the guy that shifts under the gauge transformation. And what we're doing is constructing, already, of course, what Stuckelberg did was he constructed the massive theory in a gauge invariant way without needing a Higgs field, but of course then it's non-renormalizable. And so what we're doing here is constructing the analogous thing for the massive spin 2 case. This is an effective field theory in Stuckelberg form, but ultimately we would like to imagine that there'd be some natural way to realize this from some kind of Higgs-type mechanism, or mass generation in the Schwinger sense, one of those. But that, yeah, we don't know how to do that.
Other questions? Okay. If not, let's stand.